Good afternoon, everyone. So, can we start?
Sir, yes, sir.
So, who wants to start the first presentation? Hello, can you hear me?
कैसे हम लोग कर लेते हैं
Yes, sir.
Okay, please start.
wait.
Okay, okay.
Hello.
Yes, sir.
Yes.
Hello.
Uh-huh.
Is my screen is visible?
Yes, yes, visible.
Okay. So, Ayush.
So wait for a second. So good afternoon, sir. The topic on which I am going to present my presentation is image restoration. Our team member are Kunal Lal, Shubham Kumar, Sanki Gupta, Shubham, and me itself. Open the second slide. At first, we are solving the problem which we are facing. So basically, image restoration means improving degraded images such as hazy images, rainy images, blurry images, and noisy images. So why it is difficult? What are the problem we are facing? That modern models use self-attention to solve this problem, which is also known as transformers, where each pixel compare with every other pixel. So which helps in understanding global relationship. For example, if images has n pixel, so it got compared with every other pixel. So there are total n square comparisons. Now the problem is it is very slow for high resolution images. So so our paper aims to design a model that is faster, which has own linear complexity, accurate, and lightweight. Now, I would like to hand over second slide to Kunal Lal.
Thank you move to this citation. Okay. I will talk about the code idea. In normal attention, every pixel compare with every other pixel using a complex exponential function. This gives accurate result, but is very slow. To make it faster, the paper uses math trick called Taylor expansion, which replaces the complex function with a simpler one. This reduces complexity a lot, but the shortcut make the model to lose its ability to focus on important pixels. So the paper again introduced TMSA, that is token-based multi-head self-attention, which added a special sharpening function to bring back its focus while keep the computation fast. Now I would like to recap what I have been talking. The problem with normal attention was it uses complex math which need too many complication calculation, which was very slow. To come up with the solution, we first go to Taylor expansion, which replace the complex function with simple approximation, which make the attention fast, but but the shortcut make the model lose its ability to focus on important pixel. So again, we got the TMSA to add the sharpening function and make important pixel stand out again. I, I will hand out the next slide to Shubham Kumar.
Yes, sir. Let me walk you through how our model works step by step. So first of all, we start with an input image, pass it through an encoder to extract features, process it at multiple scales, and then reconstruct a clean image using a decoder. Basically, for it, we use unit structure for encoding and decoding image. Encoder to extract features, bottleneck to understand the image deeply. Decoder it is used for reconstruct the image, multi-branch design to capture different scales, deformable convolution it is used for to adapt to shapes, and positional encoding to know pixel location, a skip connection to keep fine details, and residual learning to predict only correction. Next, Shivam Tullu.
So
This
how
is
everything connects.
taken by Scientific.
How everything connects. Our model takes an input image and processes it through multi-scale branches to capture features at different levels. Then the TMSA++ attention mechanism efficiently connects important pixel relationship, allowing the encoder to learn a strong and detailed representation. The decoder constructs the image while skip connection helps restore fine details that might be lost during the processing. As a result, the model achieves faster computation, better focus on important regions, and produce high-quality restored image. Next slide, Mr. Gupta.
Dataset result and limitation. The model is tested on different types of images, basically haze, rain, blur, snow images. The performance is measured using matrices like PSNR and SSIM. PSNR, the full form, peak signal to noise ratio. It is a metric used to measure how close a restored or compressed image is to the original image. Basically, it compares the original image with the processed image, the output, and tells how much noise or error is present. The actual mathematical formula to calculate the PSNR value is 10 log base 10 of max square by MSE, where max is the maximum pixel value, which was usually 255, and MSE, that's the mean square error, which actually the difference between the original and output image. The SSIM that was used is to measure how visually similar a restored image is to the original image. Basically, SSIM, that the structural similarity index measure, it checks the structure, the edges and shapes of the image, the brightness and the contrast. Basically, it compares the image within a range from -1 to +1. If the output is closer to +1, it means that the output is better. The image is structurally good, as well as it is bright enough, uh, and it has a proper visuality. Then the result, it's high quality restoration with faster than traditional attention model, and it also work on multiple tasks as different types of hazy blurred image. The limitations of our project, its approximation is not fully exact, and the model architecture that we are using is too much complex, and it's need GPU, where it is speed up the deep learning model with image processing and matrix calculation, as we use PSNR and SSIM. So there is huge number of calculation uh, to processing of large image data. Thank you, sir.
Thank you, everyone. So the presentation was good. Okay, so so here you are doing a sort of, so softmax was the original like function, and instead of using directly softmax, you are trying to approximate that function, right?
Yes, sir.
Yes, sir.
Sir. Yes, sir.
Okay, so one thing that like you can do is that instead of using Taylor series, that what they have done here, you can try with page approximation, PADE, page approximation. So this is one way of doing approximation of any function. because your softmax is ultimately an exponential function, e to the power x divided by summation of e to the power of x. So if I expand e to the power x, it's like going to infinite, infinite. So somehow you have to do approximation.
Okay, sir.
So instead of using Taylor series, you can use like Page's approximate, PAD. So that's even better than the Taylor series. So then we can check that whether we are getting even better result, since we are also doing approximation. So whether our result will be better than the proposed one. Another modification which you can do is here they are using multi like scale. Instead of having multi-scale, you can go for cross-scaling. That means extracting information between different scale of information. So instead of like taking just like different scales, so try to extract information from among the multiple scales. So that's what is cross-scaling.
So can you explain it once? What is cross scaling?
So multi-scale is like, so you have suppose 5 cross 5, like you are taking a 5 plus 5 kernel, you got one output. Again 3 cross 3, 7 cross 7, like different scale, and you are getting an output at different scale. What is cross scaling is, so like you have a 5 cross 5 and you have a 7 cross 7 output. Instead of directly using those filtered output, you extract features among them. So you look into the features which are best, and then you use only those features instead of using that all 7 cross 7, 5 cross 5. That's what is cross scale. So like you're like you're performing a cross operation between multiple scales.
Okay, sir.
So I will send a paper, like there's a paper for that, the cross scaling. So that, I mean, instead of like using multiple scale, so try to use cross scaling because that may give you much better output as compared to multi scaling.
Okay. Okay, sir.
Okay, sir.
And regarding linearity, yeah, I mean, you cannot go below linearity. So like at least order of n will be there. There you cannot do. Um, Regarding transformer, like I'm planning on a cross transformer. So like instead of using like it's similar to shifted window, only thing is that a modification to shifted window I am proposing. So like uh, we are so within the win what I would like to say is, so like in swing transformer, we have within window attention, and then cross window we are performing attention. So instead of that, we can like perform within window and selecting certain windows where we can get like important information instead of using all the cross scale windows. So that I will give you a paper for that. So like how to perform a cross window transformer. So these three, please take into note, like we should like implement these three in our model. One is paid approximate, another one is cross scaling, and the third one is cross transformer.
Okay, sir.
Okay.
Okay, sir.
So like if anyone have any query, you can ask. Like no query.
So,
Okay.
No, sir.
Yeah.
sir, I have a question, sir. What is, sir, we are using transformer initially.
Correct.
So, but why you are choosing for cross transformer instead of a normal transformer?
Transformer is so like so we started with VIT. So VIT was of order of n square, then we shifted to a Swift transform, which is order of like or n in terms of like complexity. So like cross transformer will further reduce your complexity and will try to give you much better output. So ultimately, like our objective is to reduce the time complexity and to get better like result in terms of PSNR as well. That's what like that's why like because swing transformers came in 2021. After that, many transformers further have come like which are giving much better output compared to swing. That's why.
Okay, sir. Thank you.
Okay, so next, so two more groups are left. Okay, so Ayush team will be performing at the end. So then the remaining one. So one.
Sir, can we start?
Yeah, please, please.
Okay, sir. Then I'll be sharing my screen,
Okay.
sir. Okay, sir. Good afternoon, sir. Good afternoon, everyone. Our team consists of me, Rishabh Dhara, Antanil Gupta Bakshi, Polomi Das, Trideep Devnath, and Aniksha. And our given paper was about vision transformers. This is a very popular paper from 2021, which basically established that convolutional neural networks can be outperformed by transformers themselves. This paper is
Rishabh,
named.
sorry for disturbing. Like, what is the
Yeah,
title of your work? I mean, the project title.
sir, we haven't gotten project title yet though. Like for now, I think it's vision transformer. Like we are planning on a hybrid transformer between that also uses convolution in the final layers.
No, but I must have given some like specific area where we will be working.
Sir, we only got two papers, one including Swin and one including vision transformers.
Sir, I would like to interrupt. I think you gave us image recognition through a drone camera.
Yeah, that was cancelled.
Exactly. Yeah.
Yeah, yeah, yeah.
Oh, yes.
So I think you should focus on that. I mean, the specific paper that I gave.
So this is the paper you gave. You gave us two papers. One was with this, and I think the second one was Swin transformer.
No, but apart from that, regarding this drone like detection, like that also I have given. Just check. Let me check the group. Just a minute. What is the name of the group?
So it's CSDL's final year project team.
Okay, okay. Yeah, it's there. It's LI point SR self-regulation, self-regularized point supervision. So the paper has been there in the group. So it's point SR self-regularized point supervision for drone view object detection.
As simple as that,
That
আমি
was the
কথাটা
paper.
বলছি তোদেরকে কেউ কিছু না পারলে we
I
are
think you missed
definitely
that.
one of
I think
coordinator
yes.
ঠিক আছে এটা নিয়ে কোনো
Problem.
প্রবলেম হওয়া উচিত না
So like,
Sir-
so this presentation is regarding only VIT, right?
Yeah, sir.
Yes,
it's
only
very
VIT, sir.
So, because VIT we have already covered, so I don't want to waste the time here. So okay, no problem. So at least we like read that paper and Monday, like maybe like next day, like so you group can give a presentation on that.
About the drone part, sir?
Yeah, the drone
sir.
detection. Okay.
Absolutely, sir.
Okay.
Okay, then, sir, I'll stop sharing the screen for now.
Yeah.
Okay, then. Sorry, sir.
Okay.
Hello.
Yes, you can start.
Sir, is my audio clear?
Yeah, it's absolutely clear.
Yes, sir. So our topic was towards the enhanced in printing. So so our team are means our team member includes Anushka De, Avinanda Guchait, Ayush Kumar Sao, and Taposhi Gare. And so so basically the inpainting refers to the process where given a marked region we have to predict given a marked region and the unmarked context we have to predict the unmarked region based on the we have to predict the marked region based on the unmarked context. So the image inpainting model can be grouped into two major classes, namely the reconstruction based models and the generation based models. So each having its their own pros and cons. So the reconstruction based models are refers to those models which which predicts the masked region using the unmasked region only. And the pros are that they are highly context stable and they avoid hallucinations. But the disadvantage are that they produces blurred results. Like we can see in this picture, there are some like pixelated portions or the pixelated predictions, and they have low fidelity. And the fidelity refers to the uh, precision with which a model retains the fine tune uh, means retains the actual context of the actual image. Hello, hello, hello.
Yes, yes, you can continue. Done.
No, no, no. So
I'm here.
and the generation portion refers and in the generation model there is given the random noise along with the unmasked context. We try to generate the final image, and the advantage are that the generation based models have higher diversity and higher fidelity, whereas the cons is that it often hallucinates. So hallucinating means that the model creates some objects that is totally off from that actual image. Like in the given example, we could see that the masked region is that this portion of the tree, but the results came out to be actually a dog, which is totally unexpected. So, so what this paper try to explain is that can we have best of both worlds? That is, can we get a image that is highly context stable as well as highly fidelity? That is, they could generalize as well. So, so the state of art, which is the which is the stable diffusion model, have these two problems of hallucination and inconsistency color. So the hallucination problem was handled by the aligning the MAE prior with the stable diffusion. So the author find out that if we somehow give the masked prior to the stable diffusion process and then generate a and then generate the picture, the stable diffusion has a better context rather than simply having the textual context only. What I mean to say is that if there is an image with masked region, and if we pass that image to the MAE, the MAE outputs an outputs an image with the masked regions being blurry at the initial stages. Okay, and if we then add the noise and denoise it, then it results in a picture which have a blurry portion in the masked region. So the author tries to mitigate this by using by feedback, means giving the feedback of the MAE as a prior to the latent generator of the VAE, sorry, of the stable diffusion. So what they does is they pick the image, remove the means they remove the masked portion, and given give that image to MAE to predict the image, and the MAE produces an image which is kind of pixelated, and this pixelated image is given to the latent generator as a prior. Now the diffusion model have a better not does not have to rely on the text solely. They have a better context understanding, and hence as a result they does not hallucinate. So this architecture helps the in painting model to avoid the hallucination problem. And then comes the another issue of the in painting, that is the color inconsistency. So often with the generated image have color shifts that is they produces a smear like stresses. We could though I don't think it is clear, we could see that the masked portion leaves certain smudges like things here in the image. And the other thing is that uh, this image, these smudges are quite acceptable when we are generating the image from sketch, because the shifting of the colors is consistent across, right? But in case of in painting, the shift is quite noticeable. We could figure out that there is a darker portion, and in the this region there is light, some lighter shades. So this is kind of unacceptable in case of in painting. So how the author comes out to with this solution is that they figure out that there is some kind of loss in the way that is included in the stable diffusion process. So what happens is that the latent diffusion and the rectified flow models, which are currently in use for the this kind of task of in painting, performs all the generative process in the latent space, and then translates that generative process to the actual image space, right? So the author explains that with each iteration of the VAE, we could see that there is a color shift with each iteration. If means from here to here there is one iteration, there is not so much of noticeable color shift. But as we proceed further in the last of reconstruction, we could easily detect that there is a huge color shift. So they try to mitigate this problem using the color augmentation and latent augmentation. So they take the origin, so means harmonizing while decoding. So they try to harmonize the original picture while in the decoding process. So they pick the original image and kind of given a wide variety of augmentation of colors, and they give this whole data set to the encoder, which then propagated to a decoder. So now the decoder have this augmentation, and and further we provide this unmasked region and mask. So this unmasked region will tell the decoder that we are interested in the image in the color, uh, in in these colors, means the original color will be, we will try to make the model learn through the unmasked region, and we are giving them the decoder the reference that this could be some possible colors, but we have to pick this color, and then through the feedback loop this decoder is being trained. So this process turns out to be working in certain good amount of cases, but there is even though there is still some losses is there. The problem turns out to be the latent generation is not at all perfect, and they need to count for the information loss in the unit, that is the that is in the stable diffusion, if I means like in this region. So they came out with the latent augmentation. So what they did is they simply add this portion. All the other things from here to here are uh, taken from the color augmentation part, and they added this portion for the latent augmentation. So what they does is uh, they feed this augmented images to the diffusion model, 50% of the these images to the diffusion model, and they pass the 50% simply to the encoder. Means the encoder have 50% of the uh, diffusion output, and 50% of them are simply given to the decoder, and the other process are simply the same, that is we are providing the actual image with unmasked region. So this helps to distinguish the information loss and the generation loss, and the conditioning of the means we are providing the full image, this one, and certain portion of the color augmentation. So this helps to distinguish between these losses, the information loss and the generation loss. So this total architecture helps to mitigate the color inconsistency problem in the image in painting. So in the finally we have a decoder uh, which could mitigate both the hallucination problem as well as the inconsistency problem. And the whole framework is named Ashoka, that is aligned stable in painting with unknown prior, and they are capable to generate a good generalization as well as they are able to have the textual generation process. And in the actual paper they have covered given two metrics. I don't uh, recall the name of the two metrics. And they in the experimentation process they have kind of compared with many of the previous diffusion models as well, and other like imprinting and other models as well. And it turns out that this architecture uh, performs quite consistently in overall process. That's all. Thank you, sir. Hello. Hello. Did I make that much boring? Hello, hello.
Sir, you're muted. You're not audible. If you're saying anything, we can't hear you.
I think I left the chat.
Okay.
Minute. Very sorry. Somehow, like I was not able to unmute myself. Can you hear me?
Yes, sir.
Yes, sir.
Yes, sir,
Yeah,
you
yeah.
are.
I saw the whole presentation.
Yes, sir.
Presentation is good. One thing, like so, when you're like performing the mask autoencoder, there you have provided two outputs. So, like like how you're getting two output from the mask autoencoder, like in the starting slides, almost in the starting one.
Yeah, this one.
Yeah, here. So like this is the same thing in the next slide. If you go to the next slide,
Okay.
no, no. I mean the architecture.
Uh,
Yeah. So here, like from the mask autoencoder, you got the output. Then you are passing that output through an alignment and generating two output. Is that, I mean, the two output which you have shown previously in the previous slide?
hello. No, sir, that's not the case. So basically, uh, Amaze itself can able to generate the marks portion. Okay.
Correct.
So this marks portion, if we add a noise and denoise it, then the stable
Mhm.
diffusion will generate. So this is the output, and this output
So
is
this is the output using stable diffusion.
yes, sir, stable diffusion with
Okay.
MAE as the initial latent.
Okay.
Okay, then what? Then the author, then what they does is they took this as a prior. Okay,
Okay.
means a kind of
Okay.
hunch, as a kind of hunch, which is then provided to this latent generator as an
No,
alignment.
like here the latent generator is getting two output from the alignment. That I didn't understand. Like how it's getting two out. I mean two input. So like mask autoencoder gave it output and now it's passing through alignment and then it's generating two, like that I didn't understand. Like
So,
oh, like
sir,
what is
means I am not sure about this, but I think
okay.
there is a kind of the embedding of this picture and the positional embedding also is there. That's why I think there is two input.
Okay.
I think so, that I don't confirm, right?
Okay. Yeah. So one thing you can do is here is, I mean, stable diffusion came very early. After that came smooth diffusion. So that's, I mean, or more advanced version of the diffusion. So if you can somehow replace the stable diffusion with smooth diffusion, and then you can see like whether you are getting a better output or not.
So
And one more thing is, yeah.
sir, this paper, what I have read from the paper, this PPT covers only that. Don't have added anything in this PPT.
Like the code must be available.
The code is there in the means the PDF itself. There is a link which have the data set, and I don't think so. There is code, maybe there is code. I haven't seen the link. There is data set.
Okay. So if the code is available, try to replace that, I mean, the standard diffusion with smooth diffusion, because smooth diffusion came later. So that must be more advanced than the standard diffusion.
Okay, sir. Let me.
So there one thing, and another thing is that mask autoencoder again is very like old. Like after like mask autoencoder is based on VIT.
Yeah, there is
so with the
code, I
complexity
think.
of order n square.
There is code
Yeah.
in the data set. There is code.
Correct. It must be GitHub code, right?
Yeah, yes, sir.
Because from TMSL I cannot access GitHub. Like I even asked the authority, but still they didn't reply to me. I don't know why. So is that the full code available in GitHub, or like it's just like an executable file?
I don't know.
I don't know if they have released the full code.
I think there is full code only. Yeah, it seems like there is a full code, sir.
Okay, no problem. So like just go through the code if it's fully available. So otherwise then we have to like look for the code. So like just keep in note that we can try, like we should try replacing the stable diffusion with smooth diffusion. One thing, and if we can somehow replace this mask autoencoder with an like better autoencoder, because the complexity, like if I try to run a very high, like large size image, and using this mask autoencoder, it will take very large, like huge amount of time. So that two things we should take care of for the time being, because diffusion is a very challenging like task.
Sir, I think I need to go through the architecture little deeper as this.
Yeah,
PPT
that's actually a good thing. Like everyone should like do, like you should, like the whole point for all the paper like members, that you must read the latest paper that I have provided in thorough detail, so that you should able to understand each and every nitty-gritty. And another thing that I will again like write to each of the group, that whatever the code is available of those paper, at least write that code again, so that you should be able to understand what are the different functions that will be required. Otherwise, like when we start writing the code there, we won't be able to understand like what functions we can write.
Sir, a problem that I faced while going through the paper is that in the paper there is kind of superficially given, okay, this is a VAE or this is MAE, and in order to understand that, we have to go quite a bit. Like we have to start from latent space. What is
Because they
VI?
cannot explain these in detail in their own, because these papers already got accepted. So they assume that you have read this paper and you know everything about the past paper.
Yeah, that's why it's quite difficult to go through this paper.
Correct. Yeah, that's because that's what we always do. So whenever we get like a link for another paper, then we have to like study that past paper to understand this thing. Otherwise, you won't be able to understand.
Yes.
Yeah.
So
So
sir,
it was the presentation is good, very good.
what should be our next step? Like,
so next step now it will be that, I mean, the first thing you must do, one must do is like practice this code. So like whatever the latest paper you have got, write that same code, like just looking like each and every line. So just copy that each and every line by typing. Don't use Control-C, Control-V, so that you get hands-on with the torch and like how the programs will be written. because we have just done the simple VIT and swing transformer. That's very basic thing. Because once we come to the origin, like actual program, there are like lots and lots of like detailed information will come. So the first like task is for everyone is whatever the latest paper that you are working, if the code is available, just start with the training part, like how the training is going on. So building each and every layers of the model, and then write exactly whatever the code is available. So write on your own. Don't use Control C, Control V, so that you can get practice of writing the code. So once you are like familiar with this code, then we can modify their code to our like as per our wish. Okay.
Okay, sir.
Okay, so that will be your next task. So once you are ready, like you should tell me that yes, you have completely like executed their code, and like line by line you have written the code on your own. So then we can start towards like modifying their code. So that will definitely take some time. So like start writing their code. And that is for everyone, not like specific group. So that will be your next task. So and then we like, yeah. So whatever like changes I have like said to the groups, please note those changes so that once you are like acclimatized with the code, then we will start modifying like one by one at a time, because we won't modify all the code like in a once, because then we have to check whether the novelty that we are trying to introduce in our work will work or not. Because once we suppose get good result, then we have to justify our good result through evaluation study. So I don't want to start directly to the like main program. So one by one we will make the changes to the code and check its output. So if you have any queries, you can ask now, because the next target now is code writing.
Sir, you have told us to use the soothing, what you have said, the soothing diffusion, like smoothing diffusion, something like that, right?
Yeah, smooth diffusion.
Smooth
So what you have written as what I assume is stable diffusion.
Yes, sir, there
So
is
after
stable
stable
diffusion.
diffusion came smooth diffusion.
So
So instead of stable, we will try to use smooth diffusion part.
the paper was kind of published in the 2023, and after that,
Correct. So yeah, so like smooth. So first came to stable diffusion. After like 1 or 2 years, then came smooth diffusion. SMOOTH, smooth.
but
So we will try to replace this SD with like smooth, like this kind next S.
okay, sir. Okay.
Okay. Okay. So let me know like when you are ready for the next meeting. So like then we will arrange the meeting. So before the next meeting, you must be like familiar with these respective codes. In the meantime, if you have any query, like any doubt, then like in the class, definitely we can have a short discussion. And definitely like from next week, definitely your FSP is starting. So you must be coming daily school, college. So there also like whenever we get some time, we can have a talk.
Okay.
Okay. Okay, bye. Good afternoon.
Okay, sir.
Okay,
Thank you. Bye. Bye.
thank you, sir.
Thank you, sir.
Thank you.
Yeah. So I think uh, the presentation does not gone that way. We- the reason is quite simple, that I don't have the depth, right. Uh, let's see how can we go deeper in this architecture next. Till then, bye.